Hello friends, today we will discuss in detail about the combinational circuits. Let's start understanding the topic. So here is the agenda of today's session. We will cover what are the combinational circuits, then various examples of combinational circuits, and in the end we will focus only on the adders. So we will try to discuss both half adder as well as full adder in detail about how the logic circuit diagrams can be designed for half adder and full adder as a combinational circuit. So, as we discussed in the previous session, what are the combinational circuits? So, these are nothing but the interconnection of logic gates. So, this is the basic key term being used in the combinational circuits. The rest thing is that the output of combinational circuits is purely dependent upon the input variables we are providing at the moment, right? So the here is the block diagram which consists of n number of input variables which are responsible for yielding the result of m number of output variables. The explanation about these n and m bits for input as well as output is briefly explained in the previous video. So you can check out that too if you have any doubt in this particular concept. Otherwise, the only thing to remind here is combinational circuits include only the logic gates, and these are the simple circuits which are existing within the digital machine. Next are the examples of combinational circuits. So there are many examples. These are not limited to these five or six examples only, which I have mentioned in the slide. So you could include the adders to be part of the combinational circuit. You can include decoder, encoder, multiplexer, demultiplexer, all as a part of combinational circuits. The reason behind why I'm calling them combinational circuits are that these all uh, equipments or the components are able to work with the combinations of the logic gates. So this is the sole concept behind providing these as an example. Otherwise, within the computer machine, if any of the circuit is designed using only the logic gates, then we will call them as a combinational circuit. So let's discuss in detail about the adders concept, how adder is a combinational circuit. So before introducing you to the topic of half adder, let's have a brief knowledge of what is an adder. So as the name simplifies, adder means addition, right? So now the reason behind providing half adder and full adder here is only because whenever we are consisting of addition of numbers, right? So in the half adder, we are only consisting the two input variables. Whenever we talk about half adder, only two inputs are taken, maybe x or y, like it's been given in the truth table. And when we talk about a full adder, in case of full adder, what we are having is we are having the three inputs like x and y as an input, and there is another input which is normally been considered as the carry generated by the previous output, right? So the general key term is that in case of full adder, we are working with the three input variables. In case of half adder, we are having only the facility of two input variables. So let's understand in detail about these half adders. So half adder is nothing but a combinational circuit which perform the arithmetic addition of two bits. So this is what is to recall here, the point to remember here. The addition of arithmetic addition of two input variables is considered in case of a half adder. The next thing are there are two input variables, right? And these input variables are basically been called as agent and addend bits. Okay, this x will be the agent and y will be the addend bit. So this is again just for your understanding of the concept that in the addition we are having two variables in the name of agent and the addend. So one which has been added into x will be the addend, and the one which is to be added right? That is one which is responsible, within which we want to add is the again. So the output variables that we are able to get in case of half adder are called as sum and carry. So normally we are depicting the sum as S, and we are representing the carry as a capital C. So let's discuss about its truth table first, because any logic circuit diagram can be drawn only with the truth table. So whenever we have to work with any of the circuit, we always have to work with the truth table first. We should understand what will be the truth table of that particular circuit. Only then we can design a logic circuit diagram. So let's understand about how the truth table is working in case of half adder. So x and y being the two input variables, and c and s being the two output variables. C here is standing for the carry and s is here for the sum. So whenever 0 is added to 0, so 0 will be the sum and 0 will be the carry. When 0 is added to 1, so in this case 1 is the sum and no carry is generated. When 1 is added to 0, the result will remain similar to the previous output. Then 1 plus 1 is going to yield 1 plus 1 is 0 as a sum and 1 as a carry. So ultimately, I think we all can easily relate to this point, that 0 plus 0, 1 plus 1, how we are able to generate these sum and carry values. Now the point to understand here is how from the truth table we are able to design the logic circuit diagram. So here is the point. So what is the agenda in case of half adder? We are looking for the outputs, two outputs actually. One is for sum, another is for carry. So it means some relation I need to figure out so that I can understand which logic gate can be provided in case of sum. Same is the case in case of the carry also. I need to understand the logic, that which particular logic gate can be applied in case of carry, right? So here if I look at this particular output of the carry in case of half adder, then I can easily see that this is purely resembling to AND gate. If you remember the AND gate truth table, the AND gate is working the same way. Let's suppose this is the only gate present. Okay, so if I would say which logic has been used here, then it is very easy to understand that it is the outcome of AND gate. AND is doing nothing but the multiplication of two numbers, right? So 0 multiplied with 0 is 0, 0 multiplied with 1 is 0, 1 multiplied with 0 is 0, and 1 multiplied with 1 is equals to 1 actually. So definitely that is why I am assuming that x and y being AND, when I am ANDing, doing the AND of x and y, I will be able to lead for a carry as an output. So if we thoroughly look at this particular point, sum, how the sum is actually coming, then sum is coming like 0 1 1 0, right? So let's again understand these 2 points, x and y being this 0 0 0 1 1 0 1 1, and how this particular output of sum is resembling to which particular logic gate. So if we closely see that, then it is nothing but an XOR gate. If you remember in case of XOR gate, what used to happen was XOR was doing like x complement y plus x y complement, right? So it was actually yielding the same result. So that's why for the sum we have used the XOR gate, and for the carry we have used the AND gate. So x being the input to the sum XOR gate, y being the input to the XOR gate will yield the sum, and the same x and y being the input to the AND gate will yield the carry. So this is how the half adder works. You can quickly look at the entire truth table as well as the logic circuit diagram in order to understand the concept in more detail. So after this, there comes the full adder. So it is very important to understand the full adder here. Reason being, a little bit more concept is being used here, or you could say the structure is a little bit complex than that of the half adder. The only reason is that now it is able to take the three input values. So it is requiring three input values. That's why I could say that a bit more complexity will be there while looking for the result in the logic circuit. So let's understand how the full adder works. So full adder is again a combinational circuits that forms the arithmetic sum of three input variables. So as I said earlier, full is for the three input variables. So total three input variables and two output variables. Two outputs will remain same as it was in the half adder, sum and the carry value only. So, how these three input variables are coming in this case of full adder? Let's understand that. So, normally what's happening is that maybe in the later part of the sections when I will be describing you how the binary arithmetic works, or addition of two numbers has been done, or adder or subtractors are working, you will get to know the application of this full adder there. So for here, in this particular case, you have to understand that there are two input variables already, which is x and y. Its value is like 0, 0, 0, 1, 1, 0, and 1, 1 only. Now, what's happening is we are introducing a third variable. Now, what is this third variable? This third variable is something like कोई previously कोई input हुई जिसमें addition की and some carry is being generated there. So normally what will happen, that carry will be taken to this z. So if that particular value is to be taken here, it could be either 0 or it could be either 1, right? So we are considering that's why two cases. It could be 0 0 for carry being generated as 0, 0 0 x and y for carry being generated as 1. Same as for this. For 0 1, the input of the carry can be 0, or for the same 0 1, the input of the carry can be 1. Same is for 1 0, the input can be 0, and for 1 0 again, the input can be 1 as well. For 1 1, input carry can be 0. For 1 1 again, input carry can be 1. So accordingly, what I have to do is I have to do the sum, and the I have to do the sum of these three variables and have to generate or to test whether it is able to provide me a carry or not. So we will discuss the truth table in the next slide. So here I just wanted to explain you this concept. Two input variables being x and y represents the two significance bit to be added. The third input z represents the carry from the previous lower significant position. Okay, so this could be the case. Like again, I would take one example here to demonstrate the idea in much detail. Let's suppose previously we were doing this. Now, in the resistor, whenever we are using or storing the data in the resistor, a 2-bit data can only be stored in a resistor of size 2-bit only. Like if it is, I have to do the addition of 2-bit data, then definitely the resistor where I will be storing the result will be of 2 bits only. So my point here is that if 1 been added to 0, I will get 1. So there is no carry bin there, but 1 plus 1 will yield 0 as an output and 1 as a carry, right? So this 1 carry cannot be accommodated here. So, because reason being, it is of only 2 bits. The rule of digital electronics says that the resistors of same size can be added or subtracted, right? So, because of this, what will happen? This one, where this one will go? So, if you read again this last line, the third input Z represents the carry from the previous lower significant bit. So this is the least significant bit. This is the MSB, most significant bit. So definitely this Z one can reach to the be part of, you could say that, the next input values. So this is how this one can be used in this Z part. So if it is 0, let's suppose no carry has been generated. I have just added 0, 0 with 0, 1. So I know that the output will be 0 plus 1, 1, 0 plus 0, 0. And no carry will be there. No carrying means 0. only. So I will be considering 0 within the output. So this is how I will work within the full adder's three input values. So the explanation was about why this third input is taken and what is the significance of that. So let's understand in detail about the truth table. So this truth table is working the same way as I was explaining you. XY can be 0 0. For both 0 0s, the carry, input carry can be either 0 or 1. We are not sure. It could be any case, right? Same is for this. 0 1 and 0 1, because the carry can either be 0 or can be 1. For 1 0 1 0 case, it could be 0 1 0 or 1 as an input carry. Same is the case for the last double ones being the input values. At some time I can get 0 as a carry, and in some cases I might get 1 as a carry from the previous output value. So by providing these inputs, what I am able to get is, so I will be getting nothing but this. I have to do the sum of these three variables. So let's do that. So 0 plus 0 plus 0. 0 will be the sum, 0 will be the carry. 0 plus 0 plus 1. 1 is the sum, 0 is the carry. 0 plus 1 plus 0. So what it is going to give me? Again 1 as a sum, 0 as a carry. So 1 plus 1, 1 plus 0 means 0 as a sum and 1 as a carry. Same for 1 plus 1 here. 0 will be the sum and 1 as a carry. For 1 plus 1 plus 0, 0 sum, 1 as a carry. For triple 1, what I am going to get is 1 plus 1 is 0, 1 is going to be the carry, right? So 0 plus 1 is going to yield me the 1 as an output, and 1 will itself remain as a carry value here. So I think it is you can easily relate to this particular truth table here. Now our agenda from the truth table is how the logic circuit diagram can be created. So in order to create the logic circuit diagram, we have to actually work on the Boolean expression. Reason behind this is we just need to simplify the equations, right? So in order to simplify it, what we do is we try to look at the facts, like how this again the logic behind how the carry has been coming, and same logic is for this particular sum value. So if you have to go through the carry in case of this, then one possible expression for carry is this. So how this particular carry is generated here, let's understand that. So if you can look in the carry where I am getting 1. 1 means when there is a case, when there is a possibility that carry will be generated, right? So in that case, what was the value of x, y and z? So here in case when this 1 was generated, the carry was like x complement y and z. If something is some input is representing 0, it means it is a complemented form, because by default we take x, y or z as a 1, right? Same plus what is happening in this case, x, y bar and z, x, y complement and z, plus in the next case what is happening, x, y and z complement, x, y and z complement, plus what is happening in the very last case, x, y and z, right? So if you look thoroughly here, what we are getting, so this is something like x complement y z, x y complement z only. So it means I can take this z as a common value among these two, right? So what will be the case, x complement y and x y. So if you look here at this point, this term is representing the same thing, okay, these two. Now what about this case, xy, let's take xy common from here, and what I am getting here, z complement plus z. So if you remember that the Boolean identity, it says that z complement, a number with complement, when added to the same number, what we'll get is, it is nothing but a 1. This is the Boolean identity. Okay, you can refer the Boolean identity in the Morris Manor book. There are a number of Boolean identities given. So my idea here is to tell you that I am able to get the another value as xy. So this is how this xy and this entire expression came. So if you can look here again in detail, in a thorough manner, this is nothing but the x XOR with y, right? This particular term. So this has been more simplified here, x XOR y. And for the sum, the expression came here is like x XOR y XOR z. So once we got these two expressions, what I am able to get is the logic circuit diagram. So how the logic circuit diagram can be designed? So look at this sum back. What I need to get? I need to get three variables, but all three in XOR form. So what I did the XOR of these two inputs here, x and y, did the XOR. Okay. So whatever the result being generated here, definitely that will become the input to the next XOR, and this z as the third input value go to this XOR. So ultimately it is getting nothing but this x XOR y XOR z in the sum. But if we look here at this carry part, what I need to have? I need to have one variable as xy, one logic gate. So this is nothing but an AND gate, right? So I need a XOR 2 and I need another AND too, right? And then in the last, I need an OR gate also to do the sum of all. So how it is going? So for xy, what I am getting is, as it is simplified here in the expression, then I will be using a AND gate, okay? Then what will happen? I also need x XOR y. So x XOR y is already present here. So I need not to draw it separately. So what I have to do? I have to do its AND with the z, third input. So this value x XOR y is coming here. X XOR y, and it is doing going to be the AND with this z value, and then will yield some result. This xy will come and we will do the OR of that carry. You can again look thoroughly at this circuit diagram, that how it has been designed. It is very simple, which if you are doing it for the very first time, you need to think at, or you need to understand that how we are representing the logic circuits. Okay, so the idea is that I need not to repeat the same thing for carry, like for x XOR y I need not to design it again. Reason being, it will ultimately make this particular circuit more complex, and along with that it will also increase the cost of the circuit. So whenever we are designing the circuit, we have to focus on both parts. Cost should also be optimized. We need to optimize the cost, as well as we need to make a simplified circuit rather than making it more and more complex. Now, as I was explaining you the methodology of that sum is like x XOR y XOR z, you can simplify this expression further. You can get to know more about कि ये कैसे आया है. But my point here is that there is another method also to get the result of the same. So the another method is, we can also use the ability to work with the K maps in order to get sum and carry. The reason why I am telling you this is because K maps are responsible for simplifying the circuits in much better way. So if we can go through them, so we are having three terms, so definitely I need eight boxes. So x, y, and z is been there. So this is x complement and this is x. This is going to be like x, y bar, z bar. This is to be like y and y bar, z bar, and y bar and z, right? So this will be yz, and this will be y and z bar, right? So I was a little like, okay, so the idea is that I have all the key terms available. So I just need to refer when I am getting the one. Again, one more thing, the numbering of these boxes. So this is the very first, which is actually a zero number. I'm so sorry for being very bad at handwriting, just because I'm using the mouse, so it becomes really hard sometimes. So zero, 1, this is 2, this is 3, the number where the term is right been placed. Okay, 4, this is 5, this is 6, and this is 7. Ultimately this is the point. So my point here is, if we look in this previous truth table, this is for sum, right? So within the sum, when I was getting 1 1, there were one, 2, 3, and 4 cases only. So when the sum was equals to 1 in this case, so it was like x complement, y complement, and z, right? So let's figure out where I'm getting that x complement, y complement, and z. So this was the case. That's why 1 is been provided here. This. Okay, same if we look further, then the second case for the sum is this one. So in this case, the combination was x complement y and z complement. So x complement y and z complement. This is the second one been there, right? So same is the case when we are getting the third input value as 1 is x, y complement, z complement. So it is like x, y complement, and z complement. So 1 is coming at this particular position. And the last is there, which is x, y, and z itself. So let's understand that x, y, and z. This one here. So this is how we are getting 1 1 1 here. So the idea for K maps is that we need to make the pairing of the things. But here no such pairing is allowed. So what I am able to do is I am just directly able to generate the results. So what I am getting here for this particular one, what I sorry, we will start from this particular key term one. It is x bar, y bar, z bar, x bar, y bar, z. So this is what it is depicting. Then next is this x bar, y, z bar, right? Then again the next two terms. So we need to simplify it. Ultimately, we will get to know that this expression is nothing but this x XOR y XOR z. Same is the case for the carry also, right? So we need to write the numbers here 1, 2, 3, 1, 0, 1, 3, and 2, then 4, 5, 7, and 6. Then we need to understand that what I need to take here, which variable and which variable I will be taking here. So accordingly, I will be representing that x complement and x then along with that. So I hope you have understood this entire K-maps expression also for making the boolean for making the combinational circuits. So the ultimate or the reason or the sole purpose behind doing all these things was only to generate the logic circuit diagram. This. So it might be the case that you have not simplified it fully and you are getting some different kind of logic circuit diagram other than someone else. So it is totally okay if you have written the full-fledged Boolean expression that how you are able to get it. You might simplify it further. You can also leave it till here. But the idea is we have to generate a logic circuit diagram which should be cost effective, right? Cost should be less on designing the circuit, as well as the circuit should be simple. It should not be very complex. So both these things we need to keep in our mind while designing a circuit, as simple as it is. That's it. So thank you so much for understanding this particular session. So if you have any doubt, you can ping me. Thank you guys.